This Zoom session is being brought to you by the Fractal Cybernetic. Okay, for today, we'll be simplifying rational expressions, part 7, and solving linear and rational equations, P8. We proceed. Okay, so, we started with a rational expression. It equals a ratio of polynomials, polynomial over polynomial. Here, 1 over x is a rational expression. X squared plus y squared over x squared minus y squared. Also, x squared minus y squared over x squared plus 2xy plus y squared. Also rational expressions, and so on. Now you can simplify a rational expression the way you simplify a fraction. You cancel common terms. AC over BC equals A over B. Unless, of course, C is 0, and that doesn't work, because then you get an indefinite expression on the left. So, for example, x squared minus y squared over x squared plus 2xy plus y squared. You can simplify that by factoring. X squared minus y squared factors into x minus y times x plus y. X squared plus 2xy plus y squared factors into x plus y times x plus y. And so, here we have a common factor of x plus y, which cancels, and therefore leaving x minus y over x plus y. You can multiply rational expressions by multiplying across with the numerators and across with the denominator, and then cancel common factors. You can divide a rational expression by another by flipping the second ratio over to d over c, and then multiplying across ad over bc. So, for example, 12x to the 61 over yx over 7y to the 15th times y over 8x to the 27th. Okay, so we rewrite that as in the numerator 12x to the 6th times 1y to the 1st. Just a moment. That over 7y to the 15th. Sorry, that looks like a g. My apologies. Times 8x to the 27th. All right. You can multiply across 12 times 1 in the numerator, 7 times 8 is 56 in the denominator. We have an x to the 61 in the numerator and an x to the 27th in the denominator, and y to the 1st over y to the 15th. All right, now after some cancellation, 69 minus 27 is 34, so you have x to the 34th in the numerator, 1 over 15 leaves a y to the 14th in the denominator, and you can reduce 12 over 56 to 3 over 14. So you get 3x to the 34th over 14x to the 14th. Here we have same two expressions, 12x to the 61 over 7y to the 15th, now divided by y over 8x to the 27th. So flip this, 8y over 8x to the 27th upside down, 8x to the 27th over y to the 1st. Here we multiply out, 12 times 8 is 96, x to the 61 times x to the 27th, you add the powers and get x to the 88th. Here, 7 times 1 is 7, y to the 15 times y to the 1, you add the powers and get y to the 16th. And so you get 96x to the 88th over 7x to the 16th. Now to add and subtract rationals, well, it helps if there's a common denominator. If there's a common denominator, then you just add the numerators or subtract them accordingly. So for example, 8 over 3x plus 5 over 3x, common denominator of 3x, numerator is 8 plus 5, therefore 13 over 3x. 3x over x squared minus 9 over x squared minus 9, common denominator is x squared minus 9 underneath 3x minus 9 in the numerator. Now we can factor this all. 3x minus 9 is 3 times x minus 3. X squared minus 9 is x minus 3 times x plus 3. The x minus 3's cancel, and we're left with 3 over x plus 3. 5x over x minus 3 plus 4x over x over 3 minus x. Okay, now this is not quite the same as this. 3 minus x and x minus 3 are opposites. So we can write plus 4x over 3 minus x is minus 4x over x minus 3. Now I have a common denominator of x minus 3 underneath 5x minus 4x, thus getting x over x minus 3. Now it's a little more complicated if we have different denominators, a over b plus c over d. Well, the way you do that is you multiply above and below for this by d, ad over bd. You multiply above and below by b for this, bc over bd. And then combining like terms with like denominators, it's ad plus bc over bd. Similarly with a minus, you get ad minus bc over bd. I call this the rabbit rule because you have a crisscross, AD, BC, BD. So kind of a sound like a picture like that. I asked my students a while back what to call that shape. There were various possibilities. The TV rule, but nobody uses TV rabbit antennas anymore. The TP rule, well, but okay, rabbit rule 1 because of the rabbit ears here, and also because it's alliterative, rabbit rule. Okay, so 3 over x plus 2 plus 5 over x minus 4. So it's 3 times x plus 4 plus 5 times x plus 2 over x plus 2 times x minus 4. Now, all right, this expands out. 3x minus 12 here, 5x plus 10 here, and after combining like terms, you get 8x minus 2 over x plus 2 times x minus 4. Here we have n plus 2 over n minus 4 minus n plus 5 over n plus 4. So again, we do the rabbit cross product. N plus 2 times n plus 4 minus n minus 4 times n plus 5 here over n minus 4 times n minus plus 4 here. And okay, then we expand both these out and combine like terms, and after a bit of warbling, you get 5n plus 28 over n minus 4 times n plus 4. Now, there's complex fractions, which are fractions made of fractions. 2/3 over 5/7, or 1 over the reciprocal of x plus the reciprocal of y, or 2 over x plus 5 over 3 over x plus 1. Now, when you have just simple fractions like this, the way to simplify this is dividing by a fraction is the same as multiplying by its reciprocal. So divide by c over d is the same as times d over c, and then we can multiply across. So for example, this 2/3 over 5/7 can be read as 2/3 times the reciprocal, 7/5. And multiplying across, you get 2 times 7 is 14, 3 times 5 is 15. So the result is 14/15. Or here's a more complicated one with variables. 18x to the 5th over 35y squared, all that divided by 2x to the 8th times 20 over x over 21y to the 5th. Okay, so the top fraction, 18x to the 5th over 35y squared, times the reciprocal of the bottom fraction. So that'll be 21y to the 5th over 2x to the 8th. So in the denominator, this flips upside down. And then you multiply across, and you combine, then you factor out common factors, etc. And you get, in the end, 27y cubed over 5x cubed. There's also, that's for if it's just a pure fraction over a pure fraction. If it's more complicated things like sums of complicated fractions over sums of complicated fractions, then the best way is to rescale by product of inner denominator. So example, 1 over x plus 1 over y. This has inner denominator 1 over x. This has an inner denominator y. So I'll rescale, multiply numerator and denominator by the product of those inner denominators times xy. And that'll cancel out everything in the denominator. And here we go. 1 times xy in the numerator is xy. 1 over x times xy is xy over x, which is a y. 1 over y times xy is xy over y, which is an x. End result, xy over y plus x. Here we have 2 over x plus 5 divided by 3 over x plus 1. The inner denominator is x here and here, so we multiply numerator and denominator. We rescale by that x. 2 over x plus 5 times x, 3 over x plus 1 times x. After some multiplying and canceling, we get 2 plus 5x over 3 plus x. Here we have an example. 1 over a minus 1 over b divided by a over b minus b over a. What's that? Okay, here this has inner denominators a, b, b, and a. So rescale by ab. Multiply above and below by ab. 1 over a times ab is b. 1 over b times ab is a. AB over times a over b times ab is a squared. B over a times ab is b squared. So we have b over a divided by a squared minus b squared. Now the denominator factors to a minus b times a plus b. That's underneath b minus a. Now this b minus a and a minus b are not quite the same. They're opposites. If we flip this, b minus a, get the opposite of a minus b. That divided by a minus b times a plus b. The a minus b is canceled, and we're left with -1 over a plus b. Now we have a number of examples we'll be going over. Here we have x plus 3 over 4x squared and minus 9, and that divided by this rather barbaric fraction, x squared plus 7x plus 12 over 2x squared plus 7x minus 15. What is it? Well, first thing we do is we take this fraction and flip it upside down. 2x squared plus 7x minus 15 over x squared plus 7x plus 12. And quickly skipping over a fair amount of work involving factoring quadratics, that not being the issue of this section, and we've covered it before. I'll just briefly say that this 4x squared is minus 9 is 2x minus 3 times 2x plus 3. This, after a certain amount of work, gets you 2x minus 3 times x plus 5. This again factored to x plus 4 times x plus 3. Well, okay, x plus 3's cancel, off they go. 2x minus 3's cancels, off they go. We're left with x plus 5 over 2x plus 3 times x plus 4. And there it is. Here we have a sum. 2 over x plus 3 over x minus 1 plus 4 over x squared minus x. Oof, for some reason there's some blockage there, never mind. All right, so, well, okay, first let's write this factor this out. X squared minus x is x times x plus 1. This is denominator x, this is x minus 1, this is x minus 1. So the smallest common denominator is x times x plus 1. So let's put everything over the least common denominator. Now we'll multiply this 2 by something that compensates for the new denominator. We'll multiply this 3 by a compensator and this 4 by a compensator. Each compensator is a new denominator divided by the old one. This over this, this over this, and this over this. So for example, to the 2, we affix x times x plus 1, x minus 1 over x, and that's just an x minus 1. To the 3, we multiply by x minus 1 over x minus 1, and that's just an x. And to the 4, we multiply by x plus 1 over x plus 1, and that's just the 1. I call these factors compensators. All right, so now we expand 2x minus 2 plus 3x minus 4 and combine and get 5x minus 6 over x minus 1. Now here we have x plus 2 over x minus 1 minus x minus 3 over x minus 2, all that over x plus 2. Okay, inner denominator is x minus 1, x minus 2, so we multiply above and below by that. And so the denominator is just x plus 2, x minus 1, x plus 2. In the numerator, x plus 2 over x minus 1 times this product, the x minus 1 cancels, and we're left with x plus 2, x minus 2. Here, the x minus 2 cancels, and we're left with x minus 3 times x minus 1. And okay, we expand each of these products. We combine them by terms. End result, 4x minus 7 over x plus 2, x minus 1, x minus 2. This is something called Newton's ratio for a function 1 over 1 plus x. It's an attempt to find out the rate of change. And we have this difference, 1 over 1 plus x plus h, all that minus 1 over 1 plus x, all that divided by h. Well, so, all right, in the numerator, we cross multiply 1 times, first we pull out the 1 over h, otherwise it just gets too bulky. So it's 1 over h times all this other stuff. 1 times x plus h minus 1 times 1 plus x plus h over 1 plus x plus h times 1 plus x here. And okay, we expand, distribute the minus, cancel the 1s, cancel the x's. 1 over h times negative h over 1 plus x plus h times 1 plus x. Cancel the h's, and we're left with negative 1 over 1 plus x plus h times 1 plus x. Now, in this one, they ask about something they call rationalizing the denominator. The idea being is that square roots are a pain in the neck as is, and dividing by those pains in the neck is an even worse one. So it'd be nice if you could find a way to get rid of any square roots in any denominators. That's the trick. So, okay. The rule is a sum times a difference is a difference of squares, and that will get rid of the square root signs. So, and if root 3 plus root y is the denominator, then its conjugate is root 3 minus root y. So sums, conjugates are differences, difference conjugates are sums. So starting with this, y over root 3 plus root y, we rescale by the conjugate of the denominator. Multiply above and below by the difference of these roots. When you do that, in the numerator get y root 3 minus y root y. In the denominator, sum times difference is a difference of squares. And root 3 squared is 3, root y squared is y. So end result is y root 3 minus y root y over 3 minus y. Oops, let me stop for that one.